When you drive down a highway, your brain processes a continuous, dynamic stream of physical light and geometry in milliseconds. But to a computer, this frozen frame isn't a picture. It is a massive, three-dimensional array of raw pixel intensity values mapped across red, green, and blue channels. If we feed this data into a traditional feed-forward neural network, the architecture hits a bottleneck. The first thing a standard network does is flatten that three-dimensional grid into a one-dimensional line. This diagram outlines a deep neural network. Look at the blue nodes in the input layer. By forcing a two-dimensional space into a single vertical column, we instantly destroy local relationships between adjacent pixels. The spatial context that forms an edge or curve is lost. To solve this, engineers developed the Convolutional Neural Network, or CNN, an architecture built specifically for processing structured, grid-like data. This is a complete CNN architecture. From the raw image input to the final classifications on the right, the network avoids flattening data immediately. Instead, it uses localized filters and downsampling to extract hierarchical features, condensing millions of pixels into a mathematical probability. Teaching a machine to see is not a problem of memorizing pixels. It is a problem of preserving spatial geometry while compressing data to its most essential patterns. The primary mechanism driving this compression is the convolution layer. Looking at this detailed architectural schematic, notice the input patch on the left. Rather than analyzing the entire image at once, the network isolates a defined region. It scans this using learnable filters, or yellow kernels, sliding across the patch. At each step, a specific operation occurs. The network performs an element-wise multiplication between the numerical weights of the kernel and the underlying image pixels, summing the results into a single number through a mathematical dot product. By repeating this localized calculation across the entire image, the network generates an entirely new, transformed grid of numerical data. We call this resulting grid a feature map, shown here in blue. Because multiple distinct kernels are applied to the same input, the layer produces multiple independent feature maps in parallel. In these early layers, these maps isolate basic physical structures, like sharp edges, corners, and distinct textures. The convolution operation successfully extracts these structural patterns while retaining their precise relative positions within the original image frame. The raw numerical output generated by the convolution step is linear. If left unadjusted, the network lacks the complexity required to model real-world visual patterns. To fix this, the network applies an activation function directly to every single value within the newly generated feature map. In CNN architectures, the standard choice is the rectified linear unit, or ReLU, selected for its high effectiveness and computational simplicity. The mechanics of ReLU are straightforward. If a calculated number is positive, the function outputs that exact value. If a number is negative, it instantly clamps the value to absolute zero, establishing nonlinear boundaries in the data. The feature maps now possess nonlinearity, but they still contain a massive amount of data, placing a heavy tax on computational memory. To address this, CNNs intersperse convolutional layers with pooling layers, represented by the transition from blue feature maps to smaller purple max pool grids. Max pooling scans a subregion, extracting only the highest numerical value, severely reducing the data's spatial dimensions. By discarding the lower values, the network achieves spatial invariance. It retains the most prominent features, like a distinct edge, allowing the system to recognize that feature even if it shifts slightly in the camera frame. ReLU gives the network the mathematical flexibility to define complex shapes, while pooling forces it to compress that data, stripping away noise and focusing only on dominant, highly localized features. After passing the data through multiple successive rounds of convolution and pooling, the network transforms raw pixels into highly abstract geometric features. To make a final categorical decision, this 3D spatial geometry must be collapsed. Returning to our full architecture diagram, data exits the final pooling box and flattens into a 1D vertical vector. This feeds into a traditional, fully connected layer, indicated by the dense network of crossing lines. These dense layers perform high-level feature aggregation. They weigh the abstract geometric patterns extracted by convolutions against the potential final categories the network is identifying. The final step is the softmax layer. It takes the raw outputs of the fully connected layer and converts them into a normalized probability distribution. It calculates a distinct percentage likelihood for discrete labels, determining if the input is most likely a car, truck, van, or bicycle. This exact sequence, extracting features, downsampling, flattening, and calculating probability, is how a CNN bridges the gap between massive unstructured data and a single semantic prediction. When a CNN is first initialized, its learnable kernel weights contain random numbers. Consequently, its first predictions will be entirely random and incorrect. CNNs rely on supervised learning. We take the network's prediction and mathematically compare it to the true known label to calculate a strict error value. This triggers backpropagation. The final error value is pushed backward through the entire architecture, shown by this red arrow. Using gradient descents, the network updates the fully connected weights, labeled W2. The propagation continues, updating the convolutional kernel weights, labeled W1. However, there is a strict architectural constraint. Because pooling layers simply extract a maximum or average value, they contain no learnable weights. The backpropagation update mathematically bypasses them entirely. The network doesn't just memorize the image. It learns by systematically rewriting its own feature detectors across thousands of iterations, continuously minimizing the final output error. At its core, a convolutional neural network functions as a hierarchical feature extractor, progressively building an abstract understanding of physical data. Because the lowest level features, basic edges, curves, and light gradients, are practically identical across every physical object on Earth, engineers rarely have to train these networks from scratch. This enables transfer learning. We can take the pre-trained convolutional kernels from models built on massive generalized datasets and lock their weights in place. By freezing the feature extraction layers, developers only need to retrain the final, fully connected classification layers to apply this powerful visual engine to highly specialized fields. In medical image analysis, CNNs process dynamic MRI scans, isolating abnormal cellular structures with glowing semantic segmentation masks to aid in targeted cancer detection. In autonomous navigation, this mathematical process allows a vehicle to project bounding boxes onto surrounding cars and pedestrians, maintaining a real-time positional lock. By designing an architecture that inherently respects the spatial geometry of its input data, we have engineered a system that translates cold arrays of pixels into a genuine understanding of the physical world.